opportunity to talk here. This is joint work with Tom Trogdon, UC Irvine. So just remind you very briefly what I spoke about last week, and that is we had the following idea. There are two natural integrabilities connected with matrices. The one is random matrix theory, the interesting statistics like the gap probability, the distribution for the largest eigenvalue, are all described by functions which are themselves solutions of completely integrable Hamiltonian systems. So that's one kind of integrability. The other kind of integrability is that if you want to, for example, compute the eigenvalues of a matrix, you go to a computer, you bring up LinPack or something like that. It will be based on an algorithm or a variety of algorithms, all of which are in fact completely integrable Hamiltonian systems. So the idea was to try what happens if you put these two integrabilities together. And the way to do that, the natural way, is to look at the computation of the eigenvalues of a random matrix. So that's what we began doing. And the phenomenon which we found was that if you looked for any given accuracy and matrices of size n and a given algorithm A, and you were choosing matrices from some ensemble, we found that the time it took, the fluctuations in the time it took to compute the eigenvalue, say, to an accuracy epsilon, was universal over a wide variety of ensembles. We don't know exactly which ensembles, not everyone, but a wide variety of ensembles, provided epsilon and n were in some appropriate scaling region. So it's a little bit vague. There's a scaling region, there are ensembles, but if you're in that scaling region and you're choosing matrices from one of a certain class of ensembles, you're going to see this universality in the computation time. So this is how things go. Suppose you want to compute the eigenvalues of some initial matrix H0. Then the way it works, a very elegant idea, is you have a sequence of isospectral iterates. You start from H0. Each of these matrices has the same spectrum, or by an isospectral flow. You've got some flow, Hamiltonian flow, with initial data H0, and for each t, Ht has the same eigenvalues as H0. Then as m goes to infinity, Hm converges to a diagonal matrix, and hence what's on the diagonal must be the eigenvalues of the original matrix. And a similar thing for the continuous case. Of course, there'll be given any accuracy epsilon, there'll be a first time m, a stopping time for which the off-diagonal entries are of Hm are order epsilon, and hence the diagonal entries of Hm give the eigenvalues of H0 to order epsilon. Okay. Now, as I say, the main finding was that the fluctuations in the stopping time were universal. So just to make it absolutely clear again, we're looking at, say, real symmetric matrices, size n by n, chosen from some ensemble E, and a given algorithm A, and a desired accuracy epsilon. You let T sub epsilon n A E of H be the stopping time for the algorithm applied to an n by n matrix H, chosen from E to achieve an accuracy epsilon. And what you do is you look at maybe 5,000 or 15,000 matrices H chosen from this ensemble E, and you look at the sample average, you take it out, you divide by the sample standard deviation, and this is the what we call the normalized stopping time, or it's the fluctuations. And then what we find is if you look for the histogram for this object, it turns out to be independent of E. That's the universality which we are speaking about. That's the phenomenon.
But dependent on A.
Dependent on A. Absolutely dependent on A. Okay. And we found, so let me just be absolutely clear. For a given algorithm A, and
algorithm is deterministic.
In this particular case it is. And epsilon n in some suitable scaling region, the histogram for the fluctuation independent of your choice of ensemble. I'm not saying, yeah.
But last time we had sometimes different histograms for different ensembles, right?
No. Always the same histogram for a different ensemble. What differed is when you go from one algorithm to the next.
But follow up on that point. If I looked at a GUE and a GOE ensemble, I get the same.
Let me answer that question later.
Initially, I don't remember the answer.
The answer was that we couldn't see it in the numerics, but you'll see in the end there is a slight difference between the two. In the actual answer for this particular, there is. So you have to be very, very careful about that. Okay. So this is the phenomenon which we found. And here are two examples. So we take a very basic algorithm. It's probably the most famous algorithm in numerical analysis, the QQR algorithm to compute the eigenvalues of a matrix. And so that's going to be on the left. And the second is the Toda algorithm, which I'll explain in a while. So these are two different algorithms A. You can see you're getting different histograms. But what you're looking at here are the matrices of size 100 here. Epsilon is 10 to the minus 10. And you have here two histograms. One for a choice of epsilon, which consist of Bernoulli matrices with plus or minus 1 on the diagonal, or in the entries, and the other is GOE. So it's two different histograms, and they're plotted one on top of the other, and you see the universality emerging there. This is for the QQR algorithm. Now you do exactly the same thing, except with a different value of epsilon. You get two histograms here, but now for a different algorithm. So you see things change from algorithm to algorithm, but for a given algorithm you have universality in terms of your choice of ensemble.
You haven't explained the scaling yet, right?
No, I do ask you to look at the following. Look at log epsilon upon log n. And for example, for QR, that would be something like 10 over 2, which is 5, and that's bigger than what I think is going to be 8/3, something like that. So you begin to get a little bit idea where the scaling region is going to be. So the scaling region is going to be of the following kind if you want to see the phenomenon. So think of it in terms of phase transitions. If you look at H2O molecules in one particular temperature regime, you're going to see one phenomenon. If you look at a different, you're going to see a different. If you look in this particular scaling region, you will see this universality. Okay, so now given a particular algorithm, we can have many different ways of choosing the stopping time. We could stop, for example, when the sum of the squares of all the off-diagonal entries are less than epsilon. Or we could do what I spoke about last time. I don't want to go through it too much, this idea of deflation when it breaks into blocks. It's a different way of saying. Now, what we wanted to do now is that there were a lot of experiments which we had done, and as I'm going to say, we did a lot more on many different kinds of numerical problems. And then the issue really arose whether this is a real phenomenon or not. Is it just something which is approximate in some sense? if we measure the distributions using something like a Kolmogorov measure to see, in other words, basically an L1 measure, are we seeing that becoming small? So it was all experiment. So to be sure that this was a real phenomenon, we want to show it's a real phenomenon, we had to take some algorithm which is of interest, not something artificial, and really prove for that algorithm that you really have this universality. For a class of ensembles, an interesting class of in some particular scaling region. So the algorithm we chose was the Toda algorithm, which I'll explain in a moment, with a particular stopping time. The stopping time we chose was the one where the algorithm has the effect of computing the largest eigenvalue of the matrix, not all the eigenvalues, but the largest eigenvalue of the matrix.
And then within some epsilon.
Within some epsilon. This is the simplest, non-trivial algorithm. As you'll see, to analyze the algorithm, it's something we could not have done three years ago, because to actually prove the universality, we need to use all the information which had been accumulated up till two or 3 years ago in random matrix theory. So we need to use the most advanced information on random matrices to be able to prove it. And to do a more sophisticated stopping time, it's beyond what's known at the moment in random matrix theory. In fact, we like to turn the whole thing on its head and say that numerical analysis, in fact, is posing very interesting, useful questions within random matrix theory, which should be addressed so that one can. So that's the idea. So we're not going to use stopping time of deflation. We're going to use this other stopping time, T1 of h, which I'll explain below, which measures the time for the computation of the largest eigenvalue of a given matrix. Now, just to fill in what we did a week ago, is say we were seeing this phenomenon of universality within eigenvalue computation. So we then began to raise the issue: is the phenomenon present in other fundamental numerical linear algebraic computations? And the first thing we looked at, well, first of all, we did some more on more general eigenvalue algorithms, such as the Jacobi eigenvalue algorithms. So for that, you would get your own histogram, which for Hermitian ensembles. Then we looked at the problem of solving h equals b, hx equals b, where h and b are random. And we use both the conjugate gradient algorithm when h is positive definite, and the Jim-Rez algorithm when h is not positive definite. Again, we saw the phenomenon of universality in the fluctuations. We also began to say, all right, we began to believe the phenomenon is there in finite dimensional problems. What about infinite dimensional problems? So we looked at solving the Dirichlet problem on a random star-shaped region with a random boundary data. And again, we found there was universality there, in the sense it didn't matter which of a variety of distributions one put to give you a random region, right? Then up till this point, all the algorithms up till this point were just completely deterministic, and all of the randomness was in the initial data. Then we said, well, what happens if we've got an algorithm which is itself stochastic? Will we see the phenomenon then? And then we picked the genetic algorithm to compute the equilibrium measure of the kind that arises in random matrix theory. And again, we found this universality there. Just as a side point, which I didn't know, but I found out a day or so ago, is that Tom Trogdon and some other people had also done some experiments on the stochastic conjugate gradient algorithm, and even in that algorithm they also find the universality. So we also So here is just to show you a little bit. This is solving hx equals b, where h is chosen from an ensemble of positive definite matrices, and b is IID. The algorithm is iterative. You start from b, you go to x0, x1, and you stop for a given epsilon when h of this approximate xm minus b is less than epsilon. Again, we look at the fluctuations of h, and again we found, here you can see they're in fact, so the matrices are of the form h equals z star. Z is of sign n by n plus root n. It's a whole story why we have to pick this size here. That's, I won't get into it. It could be, and then we pick z either to be normal, real or complex, or plus or 1 Bernoulli. And what you get is this picture here. As epsilon is 10 to the minus 4 or 14.
I'm forgetting, you cannot take n by n, right? Or
you cannot take n by n, because then you find the algorithm takes too long, and you begin to have difficulties coming up because of finite arithmetic. But it's an absolutely marvelous algorithm to turn out. Tremendous amount has been done. It has tremendous amount of structure, and it's a whole other lecture about how the thing operates. So again, you see how the phenomenon looks. Okay. Then, so as I say, the genetic algorithm uses, it's not only has initial random data, but the algorithm itself is stochastic. So this begins to show a real robustness to the phenomenon. Now, just as an interesting point, there were these recent laboratory experiments of Buckton and Correll, in which they asked some participants to make a sequence of decisions comparing the geometrical properties of figures projected on the screen. And what was recorded were the decision times, tau, and plots for the histogram. The fluctuations of these time turned out to be the same for most of the participants. They also developed a model based on the pure Kuryba spin model, and they arrived at the following explicit formula, very simple, for the decision. And this, so let me just go on one step now. It's an interesting fact here, kind of very amusing, by Sagun, LeCun, and Trogdon. So they went to Google, and what you can get from Google are the times to download words. You can get, say, 3,000 words you can plug in, and you can get the times for each of them. So what they did was to get 3,000 English words, and that gave them, when they looked at the fluctuations and the time it takes for these words to appear, that is the blue curve. Then they looked at 3,000 Turkish words, that's the green thing. And this one here, FBC, is the curve which was obtained by Buckton and Correll. So what seems to be going on is that the neural stochastics in the individuals and the Ising and the Kuryba spin model and the variations in the analysis of that model and what's happening in Google all seem to have an underlying universality. So it's okay. So for what it's worth. Okay, so now to get back to what I want to speak about today is this recent work with Tom Trogdon, where we wanted to take one algorithm and really prove that you're going to see the universality. So the talk is going to go in the following way. First of all, I'm going to explain to you the Toda algorithm. Then I'm going to state our results. Then I'm going to show what kind of ensembles we are looking at. Then I'm going to make numerical comparisons. And then I'm going to write down a whole lot of estimates from random matrix theory. And I say this uses information which was obtained in the last couple of years. Then I'll give a brief sketch of how the proof goes. The proof is not a difficult proof. It's very standard probabilistic estimation once you know all these facts from random matrix theory, and then some final comments. So what is the Toda algorithm?
Sorry, can I ask a question
Yeah.
first? Did you try more simple algorithms, for example?
Yes.
Something just iterates in the matrix since
Yeah.
how fast it
Absolutely,
goes?
yeah.
Can you prove universality for
Yeah,
some reason, or
absolutely,
is-
yeah.
Oh, okay.
Yeah. So just power law, that's really. In fact, if you look at our latest paper, we state the universality for the power, just as a paragraph. But the kind of methods we use are very similar
So
to what.
is that a faster algorithm?
No. Okay, so this is how it's a very, very remarkable fact. I mean, my claim is that anybody who works in mathematical physics will have at some point in their life a non-trivial intersection with the Toda lattice. It's my claim.
All over the place.
Yeah, it's a marvelous thing. And okay, so here it is. X is an n by n matrix, real or Hermitian. This is the commutative X with B of X, and B of X is simply the lower triangular part of X minus its transpose. So B is a skew adjoint matrix, and you start off from X equals H. X minus is a strictly lower triangular part of it. Of course, if in the real case, Y star is just the transpose of Y. Now, this flow is easily seen to be global and isospectral. So the spectrum of xt is the spectrum of the original matrix, and as t goes to infinity, xt converges to a diagonal matrix. So that means that necessarily what's appearing on the diagonal here are the eigenvalues of the original matrix. Moreover, for generic H, the eigenvalues emerge ordered on the diagonal. So the diagonal will come out with the biggest one in the 1-1 position. It's a natural sorting algorithm. So the classical Toda algorithm is you run the differential equation until the sum of the squares of all the off-diagonal elements are less than epsilon squared. That's the classical algorithm. It's not the one with deflation, and it's not the one we are going to look at. Now, if we were to analyze the time t for which this to happen, we would be using information from random matrix which does not exist at this moment. It would involve the correlation between, say, the third component of an eigenvector with the 8th component of the eigenvector. All this, we need to have very precise information about what's happening in the bulk of the spectrum. It's just, and all of it jointly between the eigenvalues and the eigenvalues. It's just beyond what we actually know.
Even for something, even for something like GUE?
Even for GUE, it's complicated, yeah.
But do you know that this, is universal?
Yeah, from an experimental point of view, there's no question. So I'm just speaking about actually proving it. Okay, so what we are going to look at is the following quantities. So E of t is the sum of the squares of the off-diagonal entries in the first row. And so we want to know our stopping time is when E of t is the first time for which this quantity is less than epsilon squared. Now, by perturbation theory, it then means that the 1-1 entry of x at time t1 is within epsilon of some eigenvalue. But because of the ordering property, that is generically, it's the largest eigenvalue. So this is an algorithm to compute the largest eigenvalue. Now, even though this is the simplest non-trivial algorithm we can look at, just to repeat myself, you'll see we need to know the most up-to-date information about from random matrix theory. So we let T1 depend on epsilon, which is our criterion for for the solution, for the accuracy, n's the size of the matrix. A is the Toda lattice with stopping time t1, and E are going to be the choice of ensembles, which I'm going to show you. Here's a little bit of the history of the Toda algorithm. It's a wonderful story. Is that in 1967, Toda described the motion of n classical particles on the line under this Hamiltonian, and that, of course, is exactly the year when Gardner, Green, Kruskal, and Miura showed that the KdV equation was completely integrable. It took a couple years, from 67 to 74, for Flushkin and then independently Manakov to show that Hamilton's equations for this system, x dot equals dh by dy, y dot is minus dh by dx, can be written in lax pair form 7. In other words, in this form here. So this is called a lax pair, x and bx, provided you make the following change of variables. You're going to take the x's and the y's and assemble them into the form of a tridiagonal matrix. On the diagonal, you're going to put minus a half of the momenta, and on the off diagonals, xi plus 1, you put 1/2 e to the xi minus xi plus 1. You make this change of variables, and remarkably, this matrix here, X, solves a lax equation, dx by dt is equal to commutated x and b. Now, b of x will be a tridiagonal matrix, which has the same off-diagonal entries below the diagonal as x, and just made skew in this particular way. Now, so we know then, by general theory, that the flow x to x of t is isospectral. I mean, just think of it, such a marvelous thought, which goes back to Lax, is that how do we know that this flow is integrable? Well, it's equivalent to a lax pair, which means that the eigenvalues of the matrix X remain fixed, and hence they are integrals for that. Such an elegant idea, of course, due to Lax.
So would you say any isospectral flow is integrable?
It will have integrals given by the eigenvalues, but they may not be but they might not be enough. And for example, if you're looking at tridiagonal matrices, right? Yeah. Then the dimension of your space is basically 2n, and then you get n eigenvalues. But you can look at the flow as we will on full matrices, and then you need approximately n squared over 2.
And you don't have that.
Well, you do, but that's what we spent basically the 1980s finding. Okay.
Right, so that's still integrable. This is a tridiagonal case, but the case you described is still integrable.
Well, yeah.
In the sense that.
And it has real hidden symmetries, so you can't see. Okay, so Flushka and Manin then showed, by writing it in lax pair form, you knew it had n integrals. Moreover, these integrals were not just integrals; they Poisson commuted in the push forward of the Poisson structure, the symplectic structure that you get from the x's and the y's. So it was integrable in the sense of Liouville. The next thing was Moser showed that the off-diagonal entries converge to 0 as t goes to infinity. Moser gave a proof of that. So then, inspired by this result, and also related work of Symes on the QR algorithm, in 1983, together with Nanda and Tomei, we suggested that the Toda lattice be viewed as an eigenvalue algorithm, which was called, we now call it the Toda algorithm. So Lax equation 7 is a natural extension of the tridiagonal Toda lattice to general real symmetric matrices. There's no reason that if you write on dx by dt equals a commutative of x and b of x, that x be tridiagonal. You can look at it on full symmetric matrices, or in the end, which is what we did, you can look at it just on real real, not necessarily symmetric, and they all turn out to be completely integrable, but that's a whole other story. Okay, so what we mean by, in current parlance, what one means by the Toda algorithm, we mean the action of the flow X7 on full real symmetric matrices, or by extension on complex Hermitian matrices.
Good question. Is this is the Toda algorithm better or faster than the QR algorithm?
Everything depends on what kind of matrices you're looking at.
Yes.
So one should.
Toda better than QR?
It's going to be more complicated than that. There's a whole engineering aspect to the problem. There is a whole family of algorithms of which QR and Toda are a part, and ideally you should be engineering which of those are suitable for what kind of matrices. Okay, just to give a additional piece of information is that Toda algorithm, as I've written down, is a completely integrable Hamiltonian system on matrices. What the QR algorithm is the following. There exists a Hamiltonian and on the matrices, and it generates a flow. And if you look at that flow at integer times, it's a stroboscope theorem, you will see the QR iterates. And that flow Poisson commutes with the Toda algorithm. So that's a whole other story I don't want to. So our main result concerns the statistics of this stopping time for both invariant ensembles, so i.e. always means invariant ensembles, both real and complex, and also Wigner ensembles, real and complex. So this is a pretty broad class of ensembles. So we will describe these ensembles in detail later on. The gap lambda n minus lambda n minus 1 between the two largest eigenvalues of random matrix chosen for an ensemble plays a central role in describing the statistics of T1. Now, the following definitions quantifies the distribution f gap beta. Beta is either 1 or 2 of the inverse of lambda n minus 1 on the appropriate scale. In standard random matrix notation, beta equals 1 refers to real symmetric matrices, and beta equals 2 refers to complex Hermitian matrices. So the first definition is f beta gap. So you make this definition, you're looking at n by n matrices from one of these two kinds of ensembles, which I haven't described yet. There's some ensemble dependent constant CV, which I'll put over here. And this particular probability distribution has got a limit, which is universal. That's a universality within random matrix theory, 1 for beta equals 1, for beta equals 2. A different one for beta equals 2. Interestingly enough, this function here is related to the Pan-Levy 2 equation. So one knows.
This is just the equilibrium. This is just random matrix theory.
It's a random matrix theory. Yeah, but it's raising interesting questions. One knows quite a bit about this function here. In the case of beta equals 2, it's related to Pan-Levy 2. But in the case of beta equals 1, we don't have a good expression for this at all. So this would be one of the many challenges which the theory.
Okay, so you know that it has a.
You know this limit exists.
You know it has a limit.
Yeah.
But you can't.
There's no nice description of Pan-Levy or something like that. Yeah, exactly. So this would be the first amongst many questions which need to be looked at. Now, this is our main result. So, fix a number sigma between 0 and 1, and the scaling regime is given by this ratio here. You remember over here, you've got log epsilon to minus 1 upon log n. That was 5, which was bigger than 5/3. I should put plus sigma over 2. If you're in this region, which means if you make n very big, you've got to make epsilon very small to get into that regime. And if H is distributed according to any beta equals 1 or complex beta equals 2 invariant or Wigner ensemble, you have this distribution, limiting distribution for the stopping time. So if you pull out log n from here, then log epsilon inverse upon log n will be some number bigger than 5/3 plus sigma over 2. So T1 is really growing like log n times n to the 2/3. Now, this result, there are many things which are interesting about it. The one thing which we like to point out is that in many analyses of algorithms, even stochastic and probabilistic analysis, typically people worry and have to take into account worst case scenarios. What's the worst thing that can absolutely happen, so that very often the bounds one get are much too big. This is an exact result. It tells you exactly what is happening to the average. So I think it's a little bit unique to have such a result. The other thing which is surprising about this and really confused us initially is the following.
Can I ask, where does this 5/3 come from?
Come from the computation. So we don't. One thing which we haven't done, we should have done, is that if we're outside this regime,
Yeah.
what do things look like? It's
And then sigma. How big can sigma? Sigma can be.
any fixed number between 0 and 1.
I see.
Any fixed number between 0 and 1.
Sorry, did you say what CV is?
It's. I'll explain what it's connected with the support of the density of states. I'll explain it in a moment. But here's really the very surprising thing, which really confounded us in the beginning. Suppose I look at this matrix. And then I look at this matrix. These two matrices have got the same spectrum. But the algorithm is a sorting algorithm. So this matrix here, when you act on it with the algorithm, is going to come out very quickly, because it's going to have the bigger one here. And this one should take much longer because it has to invert the matrix. So we thought that the distribution would have to actually explicitly reflect information about the eigenvectors, which is the other. It's not just a question now. Nevertheless, the information about the eigenvectors at this scaling doesn't play a role, which was a surprise to us.
So can I understand? So this is the same F gap that you had
before.
previous,
Yeah.
except now you have different denominator, and of course it pertains to the time dependence.
Yeah. So on the right-hand side is information from random matrix theory. On the left-hand side is everything about the algorithm. So the algorithm is behaving. You look unhappy.
Yeah, sorry, what is the role of sigma? I don't understand.
Sigma is just a scaling parameter. I mean, just
but
think.
the result does not depend on sigma, so why you can just write
No,
this
because
equal
T1 is going to be chosen from an ensemble. So you're going to be choosing something from an ensemble. So for any ensemble,
yeah.
CV will be a number occurring in that ensemble. So it's telling you if you sample matrices from that ensemble, the only information which you have to put in is information about CV. It's exactly the same as in random.
Are you asking about CV or are you asking about sigma? Sigma.
Oh, sorry. I thought you said CV.
Sigma, yeah.
Sigma is just a constant.
But why you can just write that log epsilon inverse divided by log n bigger than 5/3, and that's all? Why you need the sigma?
It comes out naturally like that.
CV depends on sigma.
But I mean sigma.
CV depends on sigma?
No.
Yes, that's
No.
why I don't understand. The result
So
doesn't
we
depend.
could say it's bigger than 8/3, for example. Or
Yeah,
is that right?
Then that would be fine.
Yeah. It's just this is the way there's nothing magical
Okay,
about
okay.
it.
So because I thought maybe the one is important, but it isn't important, right?
Yeah. So what it would say.
Yeah.
So so if we just put sigma equals 1 there, right? Then that would be throwing away some possibilities, right? That's
So it's like 5/3 plus epsilon. So
yeah. Yeah.
Just a question about your stopping
Okay,
points.
but you can
So
Yeah.
in the example you wrote on the board, wouldn't both of them already stop immediately because both of them have the property that the column entries are sum up to less than epsilon? So just on the example on the board where one of them you have got the eigenvalues sorted and the other one you do.
Yeah, no, but
don't both of them the algorithms just stop?
okay. So
immediately?
I'm just suppose I put in here instead of epsilon, I put 1 1 or
Sure.
1 1 and 1 1. Just I put epsilon there so it's obvious what the
Is there any
eigenvalue.
danger that like a matrix that has sort of non-diagonal entries that are far away from 0 will converge first to something nearly diagonal with the eigenvalue?
All of that is possible, but it has low probability. It's really a statement about what is happening in a probabilistic sense. Yeah.
Sorry, I don't get it. You have limits n goes to infinity, but
Yeah.
then if n is very large, this inequality is violated.
Why?
No,
No, you've got to be in that regime.
No, sorry.
Okay. If you're in that regime. Okay. Okay. So now what it means is that if we let xc be a random variable with this distribution function, and then for beta equals 2, one can use results from Bourgade, Erdos, and Yao in 2004 to show that the L1 norm, in other words, the expected value, not just the distribution, looks like this. So if you're in the regime where log epsilon inverse upon log n is, say, 3, then you'll see that the expected value is growing like log n times n to the 2/3. We believe this is the first time one has ever obtained such kind of information, which is telling you how long the algorithm takes on the average and what the standard deviation will be. So you just put that information in here and you find, okay. So the proofs of the analogues of 13 and 14 are, it's again, if we have non-invariant ensembles for beta equals 2 or any kinds of ensembles for beta equals 1, we don't know yet how to prove these facts. We of course have the result for the probability distribution, but we don't yet have enough control to say something about the mean. And the numerical evidence strongly suggests that these analogues are indeed correct, but you can see once again we are just raising issues within random matrix theory.
But I thought you said your result worked for
Yeah.
for Bernoulli too.
Yeah. Some of the results.
That's not an invariant ensemble.
Yeah. No, it's not. And some of the results work for Bernoulli, okay, but not the result. Not all the results which I've written
So
now.
the one you have, if you go back to your
Yeah.
theorem, the slot, you're assuming invariant ensembles. So what is the assumption?
No.
Sorry, that's what I'm trying to
To
get back now.
either for
Wigner,
yeah,
yeah. it's only
invariant or Wigner.
So,
Yeah.
So okay.
Yeah.
So that's fine.
Yeah.
So maybe Bernoulli's a little bit on the edge.
Yeah, but most of the results are true. You'll see. Okay.
By invariant, you mean unitarily?
If you're dealing with a complex case, yeah, but otherwise it's or orthogonally invariant in the real symmetric case. Okay. All right. So the result also tells us that the algorithm we're looking at computes the largest eigenvalue. So you see that the largest eigenvalue minus x11 of order divided by epsilon converges to 0, so that the 1 element is within epsilon when n is large of the largest eigenvalue. Moreover, these quantities become large. So what I'm saying is this: what is BV? The equilibrium measure for the problems we're looking at are supported in a finite interval, and BV is the top. So this is telling us that x11, is close to the largest eigenvalue, but at a distance from the next largest eigenvalue, bigger than epsilon, and also at a distance from the edge of the spectrum. So this is just to interpret so here are some. Now I want to describe what the ensembles are. You see, we're looking at a very general class of ensembles. Now, these are what the generalized Wigner ensembles are, of the kind that Bourgade and Yao and Erdős look at. It's very, very general. If you don't want to look at all of these, just think about that the entries are independent IID variables. That's certainly in the class we are looking at. So I'm just rounding it down, so you see we're looking at the general class that Bourgade and these people look at. We also look at in invariant ensembles, where you have a distribution of this kind, and V is a C4 function, the second derivative is positive. These kind of conditions are really not optimal in any way, and I'm sure we could do much better than these, but it's just the ones which they quote. They have, this is enough to guarantee that the support of the equilibrium measure is one interval. You can obviously do much more, but I'm just saying when we quote results, we have to put down what assumptions they're making, and etc. Now I want to just demonstrate what our theorem looks like in the case beta equals 2, where we look at, now we get these results applied to Bernoulli and GOE. So it's GOE and Bernoulli, and then we're going to look at GOE and BOE. So tau 1 is this quantity over here, which we showed the probability that this is less than or equal to t is given by this f beta t. And we put in this gamma for technical reasons. The distribution of tau 1 and when n gets large is independent of gamma, but to make computations in finite time, we need to put this parameter in there. It's just a technical device. Now you see just how accurate things are. We're taking matrices of size 500, and epsilon is 10 to the minus 4. So you take a log of epsilon inverse, you get 14. You take the log of n, you get 2 times the log of 5. So it's in the region, and we look at 250,000 samples. So what you're looking at here are 2 histograms, one for GOE and one for Bernoulli, and the solid curve is the curve f beta equals 2t. So, what this is telling us is that it's not that we're getting overestimates; we're getting the real thing. This is a similar thing for GOE. It's a bit of a difficulty to compute F1 because there aren't good formula for it. So there's a whole technology which we need to get the F1 gap.
So you know F1, you know F1 though, right?
You don't know it through a formula. So you have to do a sampling. It's a complicated business. How we construct F1 numerically. Okay. We don't have a formula. Okay.
It's not given by one of the panels.
No, it's not known to be given by. Okay. So the first piece of information that we use, which is a very well-known piece of information, either for a Wigner ensemble or an invariant ensemble, it converges weakly to a measure, the equilibrium measure, support in a single interval. This should be the little c mu over here. That should be this CV. Somehow it's got mixed up.
Oh, okay. They're the same.
Yeah. And the distribution looks like that.
So that's the CV that also gives the distribution.
Yeah. So this is the non-universal components of the business. So for the Wigner ensembles, with the sum here, we take C's, we ensure that CCB is 1. And what we look at when we are, so this is all just technical stuff, I'm not going to say, but you do introduce these quantiles, which is very, very important. The integral of the equilibrium measure from -50 to plus 50 is 1. So if you put little n over t, where n is a number between 1 and capital N, this integral, of course, goes from 0 to 1, and you pick the smallest value of t, you call it gamma n, that is called the nth quantile. Now, it's a remarkable fact which comes out of the work of Bourgade and people like that gamma n is very, very close to the nth eigenvalue. It's a very remarkable and key fact in all their analysis. The scale, so now we introduce certain so sigma's fixed once and for all, and we look at a variety of parameters. The constant c here is just something which shifts around. We don't need to think about that. But what's important is p is a number between 0 and a third, and s is a number which is basically less than p. And the scaling region, again, fix the sigma. The scaling region is given by this.
But where did S come from? I'm lost with the S.
It's going to go into the analysis, and the p is also going to go into the analysis. Now, a different way of writing this is we say that epsilon equals n to the minus alpha over 2, where alpha minus 10 thirds is bigger or equal to sigma. It's a different way of just writing the same thing. So alpha is just this ratio, essentially. 2 times that ratio. And this is the scaling regime. Now, this is the way the, yeah.
Just check, do you actually see numerically that if this ratio is exactly 5 thirds?
That's something we should do. We don't know exactly what's going to. Okay, it should be.
Work, but it could be. It could be even lower.
It could be lower than that. Okay. Okay. So now the way the technology goes is that, as I said in the beginning, we're going to see how to marry the integrability of the Toda lattice with the integrability of random matrix theory. Where does the integrability of Toda lattice come in? It's that you can solve the Toda equation explicitly, and that will give us a formula implicit for the time t to reach an accuracy epsilon. It's a fact you get a full formula which makes the analysis possible. Now, of course, that full formula is going to involve information about the matrices and the entries of the matrices. So you have to do calculus with an equation whose coefficients are random. So how do you do that? So you do it in the following way. We look at the class of matrices, which you call G and P, the set of all matrices, such that for a given P, the difference between the second and the third eigenvalue is bigger or equal to P times the difference between the first and the second. So any matrix which has that property, we say it's in G and P. The next are a whole lot of conditions. We say a matrix which has these properties is an RNS. So S is a number, given a P, S is a number sitting here. What are beta n's? The beta n's are the absolute value of the largest, of the first component of the eigenvector. So if your eigenvector, say HU equals lambda U, and U has components U1 up to UN, then beta is the absolute value of the first component. So it's the first component of the. So this you recognize here. This is this is an extended statement that none of the first component is getting too big. This is also telling you that if you look at
the betas are the
first components
yes Of the
nth eigenvalue. The next is a statement that at least for the top two eigenvalues, their eigenvectors, first components, are not too small. So they're pretty much of that order. This is a statement about the gaps, and this is a statement that the eigenvalues are very close to the quantiles.
Yeah.
And any matrix which has this property is an RNS.
So you need all those properties.
You need this. And then the argument goes like this. So one theorem, and all these results are taken from Soshnikov, Tao and Wu, and I forget, DG, I can check for no, it's myself. And Geoff. Yeah, with Geoff. Okay, and it's telling you that if you look at the first components of the first, second, and third eigenvalues, eigenvectors, then they converge jointly in distribution to numbers x1, x2, x3, where these are IID real or complex variables. In addition, the difference between the top of the equilibrium measure minus these three eigenvalues converge jointly in distribution to random variables, which are the smallest three eigenvalues, the so-called stochastic area operator. Furthermore, with probability 1, these numbers are distinct. And all of these results are from 1913, 1914, except this one, which goes back to 2011. Now, these are the really important things. If you look at either Wigner ensembles or invariant ensembles, then the probability that a matrix has the property RNS, those four properties, goes to 1 as n gets large for any fixed S. So most matrices, when n is large, have these properties. In other words, they are not localized, and etc. The other is a statement that the matrices which have this ratio between the gaps has higher and higher probability as p goes to 0. That's again, so you know what most of your matrices look like, and you can begin your analysis. This is where the integrability of the Toda lattice comes in. This is a formula due to Moser, that if you solve the tridiagonal, if you solve the Toda lattice, you look at the first component of the jth eigenvector, it evolves in this very explicit way. Said differently, if you take its logarithm and you forget about this constant, then you see that this is just like an angle moving linearly in time.
Yeah, so you need that to control the angles. You obviously have to control the values, I guess.
Now the key point is that this quantity here, and remember we were saying when this quantity is less than epsilon squared, that's your stopping time. This can be expressed completely in terms of the first components of the eigenvectors and the eigenvalues. That's the key fact. So here it is. x11 can be expressed in terms of the eigenvalues and the first components, and et itself, you take this thing, you plug it in here. So this is really the story, because it's telling you that if you know the statistics of the first components and the eigenvalue and their joint properties, then you have a chance of being able to analyze this algorithm. If you had a more complicated stopping time, you'd need to know much more. So I'll just go through this and give you just some idea how the thing works. Delta n is just essentially the difference between the eigenvalues, and nu n is the ratio of the first components. And the first fact is that the quantity et that you want to be less than epsilon squared can be split up into two parts, epsilon 0, E0 and E1. Now it doesn't matter what they actually are, but the key fact is that both E0 and E1 are positive. So this means that E, which is the sum of them, is less than epsilon squared only if both of them are small. if and only if, and that's simplified. You don't have to worry about cancellation. The first technical lemma works like this. Given condition 0.2, that is the 4 conditions on the eigenvalues and the eigenvectors. Any matrix which has those properties has a stopping time t1 which sits in some interval.
So that's you just abstracted what you really mean, right?
Yeah. Then the second technical lemma is that if you look at this interval from there to here, then if you look at that interval, then this quantity E0 is strictly decreasing, strictly monotonic. So now you begin to get the idea how the thing is going to work. Okay. ET is a thing we want to make less than epsilon squared. And it's ET is the sum of E0 and something else. And E02 is strictly monotonic, sitting over here. Now we pick a number t star, which I'll explain in a moment. And that's approximately where we know that E0 is going to cross the line here. So what this t star is, it's a number which makes just this first term less than epsilon squared. So the whole idea is to show that everything else is small. And irrespective of what these distributions are, this thing here is going to be dominant. So the third technical lemma is that t star lies in this interval here. In other words, this number t star lies in this interval. The next point is that if we evaluate E0 at this t star, then the difference between, you remember this quantity has epsilon squared, that's how the difference between this and epsilon squared is something small. And secondly, the second term for E, so E is E0 plus E1. What this lemma is showing that is that E0 at t star is approximately epsilon squared and E1 is small. So that means E at t star is approximately less than epsilon squared. So the fourth technical lemma is that if your matrix has this property of being in the space, then the T1 you're actually looking for, minus T star, is small. So this is all deterministic, predicated on your matrix having all these properties. Now you add the probability theory into the argument, and then you show that, in fact, with probability 1, t star minus t1 over this quantity goes to 0. And that you do, if I can just give a little bit of the argument, you say the probability that this is bigger than eta is, you intersect with this space, and this is its complement. Sitting in here, you know that this quantity is bigger than eta, so this whole probability is 0. And you estimate this by just the sum of the probability of this plus the probability of this, and you're guaranteed by the general result that these two probabilities go to 0. It's a very simple, once you begin assembling everything, so that's the proof. Then what you do, the final points are really this, that t star was chosen, this should be a plus here. T star was chosen to make this quantity here, this is epsilon squared, to make this quantity here of order epsilon squared. You replace t star with t hat, which is this explicit quantity here, and you show that that is of order n to the minus 2/3. These two are the same size, so that means that t star looks like t hat, and the second probability lemma is to show that t star looks like t hat. Now you're essentially done. So just to run through it, t1 is the object we're looking at. we show that as n gets large, T1 it looks like this T star, but T star looks like T hat, and T hat is expressed purely in terms of the eigenvalue gap, and that's how F gap beta fits. So, of course, I didn't expect you to follow, but no. You see, definitely did. Right. But the idea is this, is that you have to break up your space and see how can I do this calculus if the matrix had good properties. Yeah. Once you can do that, it's not a very difficult thing to do the calculus. Then you've got to use the fact that, in fact, the matrices having good properties is a probability one event when n gets larger and larger, and that's how the proof goes. Okay, and then just to make two points, as you see, we need all that stuff from random just to handle this absolutely order 1 algorithm. If we wanted to compute, say, the top two eigenvalues, we would already be beyond what is known in random matrix theory. We would need to know something about the joint distribution of the top two components of the, together with jointly with the eigenvalues. And so it's really an invitation to the random matrix community to prove these things. And okay, I'll stop at this point.